Welcome. Hey, if chemistry has ever felt a little tricky, you're in the perfect spot. Today, we're going to break down some really core concepts into a simple, clear study guide. We're talking about acids, alkalis, and the cool stuff that happens when they get together. Okay, here's our game plan. We're going to tackle 5 key areas. We'll start with the absolute basics. What acids and alkalis even are. Then we'll dig into their properties. After that, we'll see the fireworks when they react, learn a hands-on recipe for making salts, and finish up with how chemists get these reactions just right. By the end, you'll have this stuff down cold.
So, first things first, how do we even tell the difference between the two main characters in our story today, acids and alkalis? Well, it all comes down to what they do when you pop them in some water.
And this right here is the key difference. It's super simple. Acids, when they dissolve, release hydrogen ions, that's the H+. And alkalis, they release hydroxide ions, the OH-. These tiny charged particles are called ions, and they're basically what give acids and alkalis their unique chemical superpowers. This is the foundation for everything else we're going to talk about.
So, how do we actually put a number on all this? Well, we use the pH scale. Just think of it like a ruler for acidity that goes from 0 to 14. Now, here's the crucial part to remember. The more hydrogen ions you have, the more acidic it is, and the lower the pH number goes. A pH of 7 is right smack in the middle. That's totally neutral, like pure water.
But, how you see something that's invisible? Well, that's where these things called chemical indicators come in. They're like little undercover spies that change color to reveal a solution's true identity. Take litmus, for example. Stick it in an acid, it turns red. Pop it in an alkali, it goes glue. It's a really simple but super powerful way to know what you're dealing with. All right, next up, we're going to clear up something that trips up so many people. What is the difference between a strong acid and a concentrated one? They sound kind of the same, right? But they actually mean two completely different things. Let's get this sorted out.
First up, concentration. Honestly, this is the easy one. It's literally just about how much acid stuff you've managed to cram into the water. A ton of acid in a small amount of water? That's concentrated. Just a little pinch of acid in a big bucket of water? That's dilute. It's all about quantity.
Strength, though, that's a whole different story. This is all about behavior. A strong acid, like you see on the right, completely falls apart in water. It disassociates. Every single molecule releases its hydrogen ion. Boom. But a weak acid is a bit more hesitant. Only some of its molecules break apart, so it releases way fewer hydrogen ions.
And this is where the pH scale gets really interesting. It's not a simple 1, 2, 3 kind of scale. Every whole number you go down, say from pH 3 to pH 2, means the solution just got 10 times more acidic. So dropping from a pH of 3 to a pH of 1, that's not twice as acidic, it's 100 times more acidic. That's a massive jump.
And now for the main event. We know what acids and bases are, we know how to measure them, so what actually happens when you mix them together? Well, they don't just hang out, they react in a very specific and very predictable way.
This simple equation is the golden rule. It doesn't matter which acid or which base you use, they always neutralize each other. The hydrogen ions from the acid and the hydroxide ions from the base get together and form two totally new things, and the products are always the same.
Okay, quick pop quiz. You remember what those two products are? That's right, a salt and plain old water. Every single time.
And what's really cool is that this reaction is a perfect example of a fundamental law of the universe. You can't create or destroy matter. Nothing gets lost here. All the atoms from the acid and the base just kind of swap partners and rearrange themselves to make the salt and water. Same atoms, new dance moves.
So since this neutralization thing is so reliable, chemists can actually use it to their advantage. Let's walk through the exact step-by-step process they use in a lab to make pure salt crystals right from scratch. Think of it just like a chemical recipe. First, you warm up the acid to get things going faster. Then you keep adding your base, in this case a solid metal oxide, until no more will dissolve. That's your clue that the acid is all used up. You filter out the extra solid, then gently evaporate the water away, and voila, you're left with pure salt crystals. And here's what that process looks like in action. You can see the black powder, the copper oxide, being added. Then the mixture is filtered, leaving behind that gorgeous clear blue solution. That's our new copper salt dissolved in water. And finally, after evaporation, you get those amazing blue crystals of copper nitrate.
But hang on, that filtering method only works when your base is a solid, right? What if your base is an alkali that dissolves completely in water? You can't filter out something you can't see. For this challenge, chemists need a technique that's all about absolute precision. This is the exact puzzle. How do you add just the right amount of one liquid to another to get a perfectly neutral solution with nothing left over? It's a tricky problem, but luckily it has a very, very clever solution. And the answer is a technique called titration. You use a pipette for a super accurate starting amount of the alkali, add a few drops of indicator, and then use that long, skinny tube called a burette to add the acid one single drop at a time. You watch that indicator like a hawk, and the second it changes color, bam, you stop. You've hit the neutralization point perfectly. So really, titration is the gold standard for getting this kind of chemistry exactly right. It lets chemists create a pure salt solution without any leftover acid or alkali messing things up, which is absolutely vital for a ton of different applications. Okay, let's wrap this study guide up with the key takeaways. Just remember these 5 things. Acids give H+, alkalis give OH-. The pH scale is all about measuring those H+ ions. Strength is not the same as concentration. Neutralization always gives you salt and water, and titration is your tool for getting that reaction perfect when you're mixing 2 solutions. And that's a wrap. But here's one last thing to think about. This stuff isn't just stuck in a chemistry lab. From the fizz of baking soda and vinegar in a science fair volcano to the antacid you might take for heartburn, these reactions are happening all around us every single day. Now that you know the rules of the game, where else can you spot them in action?